So today we're at Taurakura Bay at Whangarei Heads, and we've come to this shoreline here to see an extraordinary feature, this jetty standing out into the water at high tide here. It looks as if it's been beautifully made, but in fact this is a natural feature, and this is the best example of a natural jetty to be seen anywhere in New Zealand. So when I look at the rock that we've got here and look up close, I can see it's not a sedimentary rock, but it's got little angular crystals, each about 1 millimetre long, set in a matrix of finer grained crystals. And this is typical of a volcanic rock that has cooled quite quickly. And so we have a volcanic rock forming this long natural jetty. And if you notice, it's extremely straight, and it's got straight sides on either side, and in between you can see it's jointed with horizontal joints, and these are cooling cracks. So when it was liquid and cooled to a solid, we get cooling cracks formed which are right angles to the cooling surfaces, and we therefore get these horizontal columnar joints. So all these features are telling us it's a volcanic rock that appears to have intruded up along a linear fracture through here and then cooled in place to form this hard solid rock that's forming the natural jetty today, because it's intruded into softer rock, and the softer rock has eroded away on each side. So this line of volcanic rock is called a dyke, and it appears as if there was a fracture through the country rock, and the lava pushed its way up the fracture and pushed the country rock apart and then cooled and solidified. So here's something interesting. If we look down here we have the straight edge of the dyke. It's been offset by about 30 centimetres. So it would appear that as the lava came up this fracture, the fracture itself had been displaced sideways by a small fault. Here we see the rock that lava intruded into. This is a mudstone, and it's pinky grey in colour. But as we get close to the dyke over here, you'll see it's getting darker and darker, almost black right up against the side of this intrusive lava. And this is baking from the heat of that lava. It probably was for many years still molten and hot, and it was baking the rock on either side that it had come through. And it's turned it black in this instance. So on this side we have the baked rock that was intruded, and on this side we have the lava, and right at the contact here we've got a chilled margin of the lava. And that's because right on the edge here that lava would have cooled quite quickly and become a glass rather than having crystals grow. And so that glass breaks down and is softer than the crystal-rich inside, and so it's eroding away right near the edge where it baked this rock. So scientists have taken a small piece of this rock and been able to radiometrically date it at 18 million years old. So that tells us the time when this was intruded and cooled to a solid rock 18 million years ago. Now when we look closely at the rock, we can see that it's a medium grey colour, which is typical of a lava called andesite, which has a medium amount of silica in it, about 60%. Now andesite lavas typically erupt along a plate boundary, a collisional plate boundary, as an andesite stratovolcano. And back 18 to 20 million years ago, we had two lines of these volcanoes running up either side of Auckland and Northland. Now this andesite dyke here would often be part of the plumbing beneath an andesite stratovolcano. Now when we look around the Whangarei Heads area, there are many high lands, often with bluffs and big pinnacles and things. And when you go up close to those, we realise in fact they're part of an andesite stratovolcano. This dyke of andesite has been exhumed by erosion over millions of years, and originally it was part of the subterranean plumbing beneath the stratovolcano above, which has also been eroded off, but we do have remnant parts of it in the high hills around us. So we've seen the high bluffs of the eroded remnants of that 18 to 20 million year old volcano up in the hills above us here, but now we've come down to the beach below that level, and we're seeing some large boulders that have rolled down the hill and ended up on the beach, and this is one of the largest. So let's have a closer look and see what it's made of, and it tells us a bit about the volcano remnants that are eroding above us. We call this rock type a breccia. That is, it's made of angular chunks of rock. If it was made of rounded chunks, we'd call it a conglomerate. But why do we care whether some are rounded and some are angular? It's because it tells us quite a bit about how this rock was formed and where it was formed. If they were rounded, then they would have been rounded coming down a river or a stream, or in a high energy environment on a beach where the waves would be tumbling them around and rounding them. But these chunks are so angular, they've hardly moved any distance at all. Geologists also have terms for their size of the chunks. And if they're really large, we call these boulder size. If they're more like this size, they're cobbles. And below the cobbles, we get these, which are pebble size. So we've got boulder, cobbles and pebbles, all within a fine sandy matrix. All these chunks are made of the same rock type, which is also telling us something about where it's come from and what environment it was formed. These are andesite. So as we've said earlier, andesite is a volcanic rock. So it's come from the volcanic remnants up here on the hill. But here it's made of broken up chunks in this breccia. So how did this big boulder get composed of broken chunks? And this happens up on the slopes or the cone and in the vent of the volcano. As it erupts, those explosive blasts will break apart more solid bits of lava flow and throw them out. Sometimes the lava flows will come down. As they're cooling, the surface start to break apart into angular chunks. That steep-sided cone in the middle of the stratovolcano is made of a mixture of angular volcanic breccias like this and lava flows. Around here there are 3 high points made of this kind of rock, and they are the eroded remnants of the cone. So the cones would have been much higher, and so what we're seeing is just what's left behind. The base of that volcano is about 100 metres above sea level most of the way round. Now a number of those remnants have been cut by vertical fractures, joints we call them. And periodically a whole slab of that breccia up there falls off. And so we're left with a vertical face. And that's how we get some of these straight bluffs and even these pinnacles on the top of some of the highlands. So if you're actually visiting this area, this picturesque Whangarei Heads area, and perhaps when you come to the beach and you'll see a number of different rocks, if the in situ rocks are lava, they're probably intrusive plumbing beneath this particular volcano, intruding through some of the lighter coloured country rock. But if they're breccias like this, they're likely to be in big boulders that have rolled down the hill from the eroding remnants up high.